Welcome to Lesson 12 in my series on stochastic processes. We've now seen several classes of continuous time chains, the Poisson process, birth and death processes, and queues. In this lesson, we return to the general theory that applies to all of them. The central object is something called the Q matrix. It's often known as a generator. It packages an entire continuous time chain into a single array of rates, and from that we can recover the jump probabilities and the holding times for the Markov chain. We can compute the transition probabilities at any time t by taking a matrix exponential. We finish by finding the long-run behavior of a chain and then look back across the 12 lessons in this series. And there's also one more lesson on problems. So it's no new material in that lesson, but it'll have a series of problems for you to attempt. And then I also give solutions, and that will be lesson 13. So far, a continuous time Markov chain needed three things: the states, the transition probabilities, and the holding times, the lambda. The Q matrix packages all of that into one array. And this is the definition here. Off-diagonal entries are the rates of moving from one state to another. So these are the off-diagonals. Each row sums to 0, which encodes that this diagonal is basically the negative of the sum of these off-diagonal for each row. And this is just showing that each row adds to 0. Okay, so this may seem a bit abstract. On the next slide, I'll show you an example based on a Markov chain we did in lesson 9, and then I'll show how to recover the transition probabilities and the holding times from the Q matrix. I have an example here. We'll use the Markov chain from lesson 9. States are 0, 1, and 2. This is the corresponding Q matrix. And we also have that the rates are 6, 18, and 12. So for leaving state 0, the rate is 6, leaving state 1, the rate is 18, and leaving state 2, the rate is 12. So the working backwards from the Q, we can recover the Markov chain and the rates. The rates are just the sum of the off-diagonal entries, which is also equal to the negative of the diagonal entry. So either way, so this is the rate for 0, this is the rate leaving state 1, this is the rate leaving state 2. And then the probabilities, you just take the negative of each off-diagonal entry. So for example, -3 and divide it by the corresponding diagonal, and you get 1/2. The -3 divided by -6, you get 1/2. -3 divided by -18 is 1/6. -15 divided by -18 is 5/6. Hopefully you see the pattern here. Then -4 over -12, 1/3, and then -8 over -12 is 2/3. So the two representations are equivalent. If you give me the states, the transition probabilities, and holding rates, I can write down the Q matrix. And if you give me the Q matrix, I can recover the transition matrix and the holding rates. So this is a little bit more succinct because you have everything in one place. If you use this form, you have the transition matrix and then you have the rates written off somewhere else. So a continuous time Markov chain is completely characterized by three things, which I have listed here. a countable state space, which may be finite or countably infinite, a square matrix Q with one row and column per state, and an initial condition, either a specific starting state or a probability distribution over starting states if you don't know exactly where the Markov chain begins. That's the entire specification. Everything else in this lesson, the probability of being in state J at time t, the long run proportions, the limiting behavior is derived from those three ingredients. That is worth appreciating in the discrete time case, part 2. The analogous statement was that the transition matrix T plus an initial distribution determines everything, and the n-step probabilities came from powers of T. We are about to see that the continuous time analog and the parallel is very close. The role of matrix powers will be played by the matrix exponential. So it's a little bit different than just raising t to a power. We need to use an exponential matrix. We'll see that as we go through this lesson. We're going to need the exponential of a matrix in the work that follows in this lesson. So I want to define it here generally. It's defined by the same power series as the scalar exponential, which you see here, except now this is a matrix. Remarkably, this converges for any square matrix, even countably infinite ones. That surprised me when I first saw this result. So this always converges. Computing it, we can either use a diagonalization process, which I'll talk about, or we can use an online calculator. I use symbollab.com, but there's many other online calculators that can do this type of thing. The other property is if you have commutativity between the matrix, these are matrices A, B, and BA, and these are square, then e to the A plus B equals e to the A times e to the B. But you need to have this property. And then if we just take A n times, in other words, e to the n A, that's the same as e to the A to the nth power. Okay, so this doesn't generally hold, nor does this, unless we have commutativity. So in general, this is the case. We have not equal to, but we have commuting. When we have commuting matrices, we get this result and this result. However, the SQ, going back to our Q matrix, and TQ always commute, which makes the theorem a couple of slides after this possible. So we'll talk about making use of this capability in a bit. I want to talk about diagonalization on this slide because it's very helpful in raising a matrix to a power. By definition, a matrix is diagonalizable if the matrix A can be written in this form here, B times D times B inverse, where D is diagonal. Diagonal means it has 0 entries off the main diagonal. Lambda is an eigenvalue of matrix A if AV equals lambda V for some non-zero vector V. And then the key point here is A is diagonalizable exactly when its eigenvectors, these vectors V, form a basis. So if you have this property, then you can diagonalize A, which I'm showing here. Then if you raise A to the nth power, you get B times D to the n times B inverse, right? You have a lot of cancellation when you do that. And the thing with the diagonal matrix is that in order to get D to the n, since all the non-diagonal entries are 0, D to the n is just the nth power of the entry 1, 1 and the nth power of 2, 2. In other words, the nth power of all the diagonal entries. So this is very easy to compute. So that's the reason for going down this path here. The same trick works for the exponential. E to the TQ reduces to exponentiating the diagonal entries of D, then conjugating back. So we'll see that as we proceed in this lesson here. Well, in this slide, I want to talk about the semigroup property. First, you need to define P of T. It's the matrix of transition probabilities over elapsed time T. And it's given, each entry ij, is given by this notation here. A probability of starting in state I at time 0 and being in state j at time t. Eventually, we'll relate this transition matrix to our matrix Q that we talked about earlier. But first, we need a little bit of information on this matrix. So the first thing is we want to find the probability of going from I to j at time s plus t. In other words, being in this state j at time s plus t. We can sum over all the possible states you could be in at time s. That's what this is showing here. And we can write that in matrix notation like this here. And then just note at time 0 where the probabilities are 1 for being in each of the transition probabilities, I should say, from going from one state to itself is 1, because there's not enough time to transition out of that state. So you have this here. This is true because of two things. Given where the chain is at time s, where it started no longer matters. So the condition x of 0 equals I drops out in this second factor here. We don't need to track this. That is the Markov property. Second, that factor is a transition beginning at time s, again talking about this here, and lasting a duration t. And homogeneity says its probability depends only on the duration. So we can write that as P sub kjt. This is the general, well, let's say the continuous form of the Chapman-Kolmogorov equations that we saw when we had discrete time transitions. And it holds for every time homogeneous continuous time Markov chain. So that's the important lesson from this slide here. Eventually, we're going to relate it to the matrix Q using the exponential of matrices, and in particular TQ. And then we'll state a couple of theorems, 3 or 4 slides out, that relate this P of T to our matrix Q. So we'll get to that in a little bit. What I want to do on the next slide is actually describe why this term semigroup is used. It's not really essential to the flow. It's just more in terms of background information. I wanted to explain why we use the term semigroup on the last slide. If you take a set of elements, in our case, the P of T's, so it's these matrices here, it's called a semigroup if you have two properties. Matrix multiplication is associative, and these are matrices, so we have the associative property of multiplication, and we also have closure. So when you multiply two of these together, you get another element in the set. It's almost obvious. So this is called a semigroup. It actually the set of the P of T's also has an identity because P of 0 equals the identity matrix. So it's technically a monoid, but the property we're interested in is this semigroup property. There's one further property that makes something a set, a group, and that's that each element has an inverse, but we don't have inverses. Each P of T does have an inverse. The problem is that the inverse is not stochastic. In other words, the rows don't add up to 1, and it has negative entries. So the family is not closed on their inverses. Probabilistically, the chain cannot run backwards in terms of these negative inverses. The standard name is transition semigroup, even though it is strictly a monoid, as I mentioned here. Okay, so this is a bit of a side. If you're familiar with abstract algebra, you may appreciate this a little bit more, just trying to identify this with the nomenclature from abstract algebra. YQ is a derivative at the origin. What I mean by that is this equation down here. The derivative of the transition matrix evaluated at 0 equals our matrix Q that we defined at the beginning of this lesson, the rate matrix. So we want to prove that on this slide. In order to prove it, we need an alternate view of the rate matrix Q. And that's what I have here at the top. A rate is a limiting probability per unit time. So Qij for I not equal to j can be viewed like this. The probability over this small time period h divided by h, and you take the limit as h approaches 0 from above, and that'll give you Qij. And if you multiply both sides by h, you can write it this way here, where you're kind of subsuming the limit into this little O of h. So you have this here. And then we can also find Pii of h. That's 1 minus the sum for I not equal to j of Pij of h. Remember, the rows of the transition matrix sum to 1. And then we plug this into here. We get this here. And then at the beginning of the lesson, we noted that the sum of the Qij's I not equal to j equals minus the diagonal entry. So we have a minus and a minus. We plug that in here, and we get 1 plus Qiih plus small o of h. And I just realized I'm using a comma between the I and the j for the p's and not for the q's. I'm not sure why I did that, but it doesn't make any difference. I meant the same thing here. So then we can take these two results, and noting that p sub 0 is I. So you basically have 1 is the identity matrix, since you have that across the each one of these equations. You have this 1. And then you notice you have the ij and the ii. So you essentially have the entire matrix Q times h. So if you take this equation and this equation and write it in matrix form, that's what I'm trying to say, you get 1 I plus h times q, basically these two together, and then little o of h. But since p of 0 equals I, we plug that in here. Then if we subtract this from this side, and then divide by h, and then take the limit as h goes to 0, this is a derivative, right? This is the definition of a derivative of p. So this is the derivative of p at 0. This term vanishes, and this term doesn't involve an h, and you get our final result. Okay, so a bit of work, and I know I wasn't exactly precise on every step here, but hopefully I gave you a rough idea why this follows. The key step was this slightly different interpretation of Q. If you don't see this, then you're not going to get to this final result here. Okay, so this is the link. Let's continue. We'll make use of this as we go forward. I want to relate Q and P yet again on this slide, but in a different way. From the semigroup property, we have P of T plus H equals P of H times P of T, and P of T plus H equals P of T times P of H, which is what I'm showing here and here. And I'm going to use each one of these in different ways to show different relationships. Let's look on the left first. So we'll subtract P of T from both sides, keeping in mind these are matrices. And we factor the P of T out on the right. We get this here. Then we divide both sides by h. We take the limit as h goes to 0. Then this is the derivative of P of T. this term doesn't involve an h at all, so it just comes down as p of t. And then we already saw this here, right? This is p of h minus p of 0. The limit as h goes to 0, that's q. We proved that on the last slide. So we have this here. Almost the same thing here. You notice I factored the p of t out on the right here and on the left here. But you divide by h on each side again, take the limit, and you get this here. Okay, so these are called the forward and backward equations. What separates them? Only which side the identity comes out on when you factor. Matrix multiplication does not commute in general, so p of t cannot be slid past anything, and this side is forced by where p of h sits. That is just whether you split the interval at h or at t. Taking the limit inside the product is legitimate here because a finite state space means finite matrices. Both equations are solved by a matrix exponential of t of q with p of 0 equals I, which we'll get to at theorem 33 next. I have several important theorems on this slide. These are the numbers from my book, although I don't prove them here and I also don't prove them in my book. But I do give a reference to a book by Norris that goes into these proofs. And I'll put that information in the description to the video on YouTube. So theorem 33 was P of t set equal to e to tq. The semigroup property holds, and Q could be any matrix that's bounded, so the rates are bounded in Q. And then P of t is the unique solution to both the forward and backward equations. So this first part, the semigroup property holds, that's here. And this is more general than what we stated before. We were actually working with a proper matrix for a continuous Markov chain. Here, this could be any matrix Q that's bounded, where the rates are bounded. So you have this property here, and then it's also the unique solution, e to the tq, of this equation and this equation here. So the derivative of p of t equals p of t times q, and the derivative of p of t equals q times p of t. Then we become more specific to our problem at hand, our area of concern in terms of the continuous Markov chains. Q is a Q matrix, as we've defined at the beginning of this lesson, if and only if P of t equals e to the tq is a stochastic matrix for every t greater than or equals to 0. So stochastic means the rows sum to 0. So if you take a matrix Q and you compute this e to the tq, then and it's stochastic, then you actually have a proper Q matrix, and on top of that it equals your transition probabilities, which I've basically said here in theorem 35. The transition probabilities of the chain, referring to this, are the entities e to the tq. So the probability at time 0 being in state I and going to state j at time t, Pij of t, shorthand, is equal to the ij entry of t e to the tq. We also have the stationary probability for a continuous time Markov chain. It looks very similar to what we had for the discrete case. It's the vector pi, and it's the solution to this equation here, pi times p of t equals pi, where p of t is the transition function we defined earlier. However, there's another way of finding this pi, and that's the solution to the equation pi q equals 0. So we have if and only if here, which is what I stated in the theorem. Then if the chain is irreducible and has a stationary distribution pi, then the transition probabilities converge to it. So we have this limit here as t goes to infinity, the probability of going from I to j at time t units is pi sub j, and you notice this doesn't depend on the starting state I. That was very similar also to what we had in the discrete case. I did an example on this slide and the next. I took our matrix Q from the very beginning of this lesson, and then I used Wolfram alpha to diagonalize Q. We found these three eigenvalues, 0, alpha, and beta. And so the matrix D that diagonalizes would have a 0 in the entry 0, 0, alpha in the entry 1, 1, and beta in the entry 2, 2, and then 0 everywhere else. And then we can compute the transition matrix from our previous theorem. It's e to the tq. And then we just write that out as a series, as I described earlier, for writing a matrix to an exponential of a matrix. So we have this here. And then when you have this raised to the n power, you're just going to get td to the n over the n factorial, and the b and the b inverse come out on either side. And then this is just when you put in your matrix D there, since it only has diagonal entries, the first entry is going to be 1 here at 0, 0. Then at 1, 1, you're just basically, it's just the exponential function of alpha t. So you have that here, and then you have e to the beta t here. So this, in parentheses, that's what this is here. And then you have b and b inverse on either side of this. And that gives you p of t. Okay, so I didn't write out the b. It's kind of long, but I'll give you I used a row and a column of b to compute one of the entries in this matrix on the next slide. We don't need all of b or b inverse to compute just one entry here, which is what I wanted to show. You can see it's kind of ugly. The first row of b is 1, and then r, this here, and then s, and then the first column of b inverse is x, y, and z. So if you just multiply the b times the matrix at the bottom of the previous slide, the diagonalization, and then times b inverse, you'll get this formula for p00 of t. And if you plug all this stuff in, and then take the limit as t goes to infinity, the alpha and beta are both negative, so these terms go to 0, and you're only left with x, which is 32 over 85. Okay, so that's the probability of being in state 0 in the long term, the proportion of time. And the other way of solving it, sort of as a check, we can, and it's probably easier than what I've done here, is to independently solve the equation pi times q equals 0, and where the sum of the components of pi equal 1. And if you do that, you get this solution here. And so we actually get exactly the same answer in both cases. This is the proportion of time in state 0, the proportion of time in state 1, and the proportion of time in state 2. Okay, so that's our example, and that's pretty much the last technical part of this lesson and also this series. I have a few summary slides which I'll do after this. So this is a summary of all the lessons. You may have seen these already. If you kind of just jumped in at this lesson, this may be of some use to you. So the first two lessons were foundations on the Markov property, transition matrices, and the Chapman-Kolmogorov equations. This was for discrete time, these equations here. As we saw in this lesson, there's also a continuous version. Then in lessons 3 and 4, we talked about gambler's ruin, where you had two gamblers. They had a fixed pot of money, and either one or the other went broke, and we did a lot of analysis on that. Then we talked about random walks, and we noted that the gambler's ruin was an example, and these were, for the most part, one-dimensional random walks, but at the very end, we talked a little bit about 2 and 3 and higher dimension random walks. Then there was a classification of communication classes, recurrence and periodicity, and stationary distributions. We're still looking at the discrete time Markov chains, and that was in lessons 7 and 8. Then in lessons 9 and 10, we started talking about continuous time, exponential holding times, counting processes, and then the Poisson process. And then on 11, we talked about birth and death processes and queues. And in this lesson, we talked about the generator matrix Q. So that's it. There's one more lesson, which I decided to do after I had done the first 12, and that was a lesson on problems and solutions, which I'll present as lesson 13. So stay tuned for that. And if you like this series, don't forget to give it a thumbs up. And I have one more slide here that kind of just summarizes this lesson number 12. Let's look at that. So lesson 12, as we saw, was involved the generator matrix Q, which was another way of describing a continuous time Markov chain. And that was where we concluded. So thank you for watching. I have my website here, artofmanagingthings.com. If you go there, I have a list of my books. This material is coming from my book, Mathematical Vignettes, Volume 1. And the electronic version is available free on my website. You could also buy a paper copy from Amazon. Where to go next? This series has been a survey. Even though there's a lot of material in 12 lessons, it still doesn't get in very deep. The book gives references throughout. I'm referring to my book here, Mathematical Vignettes. It's just one chapter of my book that gets into stochastic processes. Queuing theory in particular is an enormous field. There's a 2-volume set from Kleinrock. That would be a good introduction. And then in terms of stochastic processes, the book by Norris and Ross, I should say the books by Norris and Ross, one book each, would be good places to get more information. I believe I referenced the book by Ross in the previous lesson or the lesson before. I forget now. You can just look at the information to the videos. And then for this lesson, I'll give you the reference to the book by Norris. Okay, so that's it, or almost it. As I say, I have one more lesson on problems and solutions that kind of cover all 12 of the lessons. So stay tuned for that.